Okay, so the following discussion is a follow-up to an example I just did. It was an example of binomial distribution. The context was that we would roll a loaded six-sided die which has a probability of obtaining a 6 of 0.4, and consequently the probability of not obtaining a 6, of not rolling a 6, of 0.6. So the example was the following. You would take the loaded die and you roll it 16 times, and then you let the random variable x, be the number of sixes obtained. The question was, find the probability that A, you get exactly 7 sixes, and B, the probability that you get at least 2 sixes. So in the example, we worked out the example, and what we did for part A is that we considered the different cases where you get exactly 7 sixes. There were a total of 16 to 7 ways of doing that, of getting exactly 7 sixes, and then we multiplied that by the probability of each individual outcome, which in each case happens to be 0.4 to the 7th times 0.6 to the 9th. What I want to do now in this follow-up, since I'm set up to follow up the example with a generalization of the method used in the example, is the following. I want to take a look at an experiment that looks like this one, but in a general context. So here's the experiment. First of all, you have a trials in this experiment, a fixed number of trials. So you have a fixed number of trials n in the experiment, fixed number of trials. It will be fixed. Like in our example, it was 16. You were rolling this dice 16 times, and each time you perform the experiment, you roll the dice 16 times. But in general, you are performing in trials. Now, each trial will have two possible outcomes: a success and a failure. In our previous example, success was getting a 6, a failure was not getting the 6. But in general, each trial has a success and a failure. Each trial has two possible outcomes. Success and failure. Those are it. Now, in our problem, the probability of success was 0.4. I called it P. So here I'm going to call the probability of success P, the probability of failure Q. So probability of success in each trial equals P. The probability of failure in each trial equals 1 minus P, which we call Q. Now, it is understood that when I say P for each trial, that P is actually a fixed number. So I would have to say P is fixed. It's a number between 0 and 1, which is fixed. So in our example, you would get the probability of getting 6 was 0.4 for each time you roll the die. Alright, so let's consider the following two questions within this context. If we let x be the number of successes, let x be the number of successes in these n trials, what is the probability that x equals k? And let's express also the probability that x is greater than or equal to k. Alright, the probability of x equals k you have to do kind of the same analysis we did in our example, where we roll our dice 16 times and we wanted like exactly 7 sixes. We'll say, well, I have to first find the probability of each outcome. They will all have the same probability. Every single outcome there will have the same probability. But let's just consider one. So let's say the first k are successes and the remaining ones are non-successes. So there is some gap in here, and there is some gap in here. There are k here, and then the remaining ones will have to be n minus k. Now, so here it goes. Successes, p, and p, and p, all the way to the last one, p. So you have that the k successes, when multiplied out, will be p to the k. P to the k power. The remaining ones are non-successes. The probabilities in each case are q's. How many of them? N minus k. Now, how many outcomes like this are there? Well, you have to ask the question. I have n spots and I want to place k successes in these n spots. Number of ways of doing that is n choose k. Now, let's consider, so that gives us a formula. This is basically a general formula for find the probability that x equals k when your distribution happens to be a binomial distribution, a binomial probability distribution. Now, second consideration we're making now. I'm getting rid of our conditions of our hypothesis. I'm getting rid of our hypothesis because when you view the video, you can always go back to view them. So now I'm looking at the second one. What is the probability that x is greater than or equal to k? So there are going to be several cases, because when you say x is greater than or equal to k, you could be saying x equals k, or x equals k plus 1, or all the way up to x equals n. Now, these are exclusive alternatives. When you think about these different types of outcomes, you realize that they are exclusive alternatives. So we can use the addition rule for probability. We end up concluding that this is a probability that x equals k plus probability x equals k plus 1 plus plus probability x equals n. This is the addition rule for exclusive alternatives. Now, here is the strategy to deal with a problem like this. If there are few alternatives, then you can just compute this out. But if there are too many alternatives, you would like to consider the probability of x greater than or equal to k in terms of its complement. So another way of expressing probability x greater than or equal to k is by saying, well, that's the same as 1 minus the probability that x is not greater or equal to k. Now, when we did our example, we ended up concluding that then that means that x is less than k. In our example here, you want at least 2 sixes, so the complement of that is either 0 or 1 sixes. And in this example that we did here, it actually was better to solve the problem this way. So you'd say 1 minus probability x equals, well, let's try it first this way. X is, say, less than k, right? That's the complement. But then you have to break it down into the cases, into the possibilities. Well, we could have x equals 0, or x equals 1, or all the way up to x equals, what's before k? K minus 1. Now, then you would use, since these are exclusive alternatives, then you will use your addition rule for probability when you have exclusive alternatives. So these are exclusive alternatives. The context of our experiment makes those exclusive alternatives. So I end up writing 1 minus probability that x equals 0 minus probability of x equals 1 minus minus probability minus the probability that x equals k minus 1. So, which do you choose to perform your calculation? They're both good calculations. They will both yield the same result, provided there is no mistake in the process. So what you do is you choose the one that produces the least amount of alternatives. Okay, this concludes the follow-up to our example of a binomial probability distribution.